I'm going to present on the topic ionic liquid-based microemulsions and its applications. First of all, what are microemulsions? Microemulsions represent a class of thermodynamically stable, transparent dispersion of two immiscible liquids which are stabilized with the help of surfactant. Microemulsion composes of three components, polar, nonpolar, and surfactant, and possesses different regions like oil in water microemulsion, water in oil microemulsion, and biocontainers microemulsion. And microemulsion possesses wide area of applications in the field of nanoparticle synthesis, drug delivery, oil recovery, etc. But there are certain limitations of the conventional microemulsion because of the use of organic solvents that limits their use in the field of biological purposes like storage of enzymes and biocatalytic activities. So to overcome these limitations, ionic liquid has emerged as a good substituent in microemulsions. Ionic liquids are composed of ions and are liquid below 100 degrees Celsius and possesses different physiochemical properties such as negligible vapor pressure, low flammability, conductive nature, thermal stability, etc. And one of the most interesting property of ionic liquid is their tunable nature. They can be tuned into hydrophilic ionic liquid, surface active ionic liquid, and hydrophobic ionic liquid. Surface active ionic liquid aggregate in the form of rod-like micelles, bilayer sheets, micelles, vesicles, or reverse micelles. And here in this work, we have formulated microemulsions with the help of nonpolar ionic liquids, surface active ionic liquids, and with the help of ethylene glycol and ionic liquids, we have formulated highly thermal stable microemulsion and characterized with the help of dynamic light scattering measurements up to 75 degrees Celsius. But visually, we can see that microemulsions are stabilized up to 180 degrees Celsius because there occur no phase separation in these microemulsions when they are heated up to 180 degrees Celsius. So further, we have utilized this microemulsion for the storage of lysozyme. Basically, lysozyme is stabilized up to 75 degrees Celsius in buffer, but here in these thermally stable microemulsions, lysozyme is stabilized up to 120 degrees Celsius and characterized with the help of fluorescence and circular dichroism spectroscopy. Herein, the peak at 340 nanometer originates due to the presence of N2 pi star transitions in tryptophan residues of lysozyme. And from the presence of isobactic point, we infer that lysozyme is present somewhere at the interface of SALE and ethylene glycol in reverse microemulsions. And from fluorescence spectroscopy, we observed the stability of lysozyme up to 150 degrees Celsius. But after extraction from the microemulsion, we have observed the circular dichroism spectroscopy that indicates the stability of lysozyme up to 120 degree Celsius. So we can infer that lysozyme is stabilized up to 120 degrees Celsius in these reverse microemulsions. Further, we have formulated aqueous ionic liquid microemulsions for biocatalysis using cytochrome C. We characterize the different regions of microemulsion with the help of conductivity measurements. And from UV visible spectroscopy, the we infers the presence of cytochrome C at the interface of bale and water in reverse microemulsion because there is somewhat decrease in the absorbance of Soret band of cytochrome C in microemulsion as compared to that of buffer. And further, the CD spectroscopy also indicates the deformed structure of cytochrome C in microemulsion as compared to buffer. And due to these deformed structure, cytochrome C has given good catalytic activity in reverse microemulsion as compared to buffer. And we have used the Beer-Lambert law for finding the concentration of the product. So, by utilizing the rate constants, we infer that cytochrome C has shown better catalytic activity in microemulsion as compared to buffer, and five-fold increased in the rate constant of cytochrome C in microemulsions indicates the good catalytic activity of cytochrome C in microemulsion as compared to buffer. So from here we infer that microemulsions act as a better catalytic medium for the biocatalysis. So finally, we can conclude that microemulsions act as a efficient medium for enzyme storage and for biocatalysis. Finally, I would like to acknowledge my supervisor, Dr. Tejwan Singh, Professor Geeta Hundal, HOD of the department, Guru Nanak Dev University, for providing the infrastructure CSIR for fellowship. Thank you.